All right, hello, welcome. This video is going to be covering the concept of neurons and the action potentials that run through them. All right, so there is some pretty complicated things that are going to be explained here, but the basics are what I hope you understand. Okay. Um, You, at this point, should know what a neuron looks like by a diagram, how the diagrams look, being able to identify the cell body, the dendrites, and the axon. And then at the end, you'll find those synaptic terminals. Now, for the explanation of an action potential, we don't need to worry about the myelin sheath. The myelin sheath definitely plays a role in the speed of the message that's sent, okay? And there is some numbers that go along with the speed of those messages. In a large diametered axon, so in a large axon, you're going to get about 2,500 impulses per second. That's 2,500 impulses per second. In the smaller ones, you're going to get about 250 impulses per second. All right. So under normal body conditions, you have somewhere between 10 to 1,000 impulses per second in the neurons. Okay. So the myelin sheath is going to work to help increase those where it's necessary, and then they are not there in place when it's not necessary. Okay. So I want to remind you, again, an ion is going to have a different number of electrons, and that is going to make it either positive or negative. We are going to be talking about sodium and potassium and calcium when we talk about the transmission of nerve impulses. And so I wanted to remind you, potassium is K, sodium is Na, and calcium is Ca. All right, so when you see those letters, you now know what they are. I also need you to understand what it means when something is polarized. Um, we don't need to worry about the physics definition of polarized. To understand these concepts, you need to understand that there's two opposites when we talk about a cell being polarized, positive and negative. All right. We're going to talk about the cell depolarizing, which means that those two opposites are going to cancel out. And I started talking about dance partners when I was explaining how the electrons and the protons are like dance partners, and whoever's left out, if there's any left over in the dance party, that is the charge of the atom. Okay, so we are going to find that these ions are going to end up balancing out at some point, removing the positive and the negative, and that's what we mean by depolarized. And then repolarized is when the opposites are restored. Okay. So interestingly enough, we can restore the positive and negative charge, but still have chemicals not in the place where they should be as what we call the resting potential of the neuron. The resting when the neuron's membrane is at rest. Okay. Okay, so I would like you to see this little example of a neuron I drew. And you can see the dendrites, I hope. Oh, excuse me. And the cell body. You can see the nucleus there at the middle. And you can see the axon. And so I drew a dark purple square around part of the axon. And then I drew two dark lines, which that is going to act as the axon. And the myelin sheath, we're going to not talk about it right now because that would just confuse things at the moment. So we are going to worry about the myelin sheath later, okay? But what we want to know is we want to know that the outside of the cell membrane is positively charged and the inside is negatively charged. So on the outside of this I'm putting pluses to show that the outside of my neuron is positively charged, okay? And with that being said, inside the neuron is negatively charged. So now we have a resting neuron that is polarized. All right? So if there's any questions about that, remember to stop the video, pause the video, and shoot me a question either in the chat of the discussion or send me an email. Whatever it is that you want to ask, please do not let your questions go unanswered. Okay? So again, we have a neuron here. We're showing the axon of the neuron. I drew the dark, bold purple lines to represent the axon, and now I've put positive and negative marks to represent where the positive and negative is in the resting neuron. All right, so it's positive outside and it's negative inside. There is a higher concentration of sodium ions on the outside of the cell membrane and a higher concentration of potassium inside. So I'm going to go ahead and I am going to add sodium. Sodium is on the outside. Now we set a higher concentration. So there is some sodium on the inside as well, but the concentration is higher on the outside. Okay, so I'm drawing lots of sodium around the outside of my resting neuron. All right, now I'm going to draw my potassium on the inside. Now remember, the charge on the outside is positive, the charge on the inside is negative. Now, all of what we've been talking about have been positive ions, but that does not mean that the inside is positive. In a resting neuron, the inside is negative. All right? So hopefully, if you have any questions, you're going to stop and ask them. Otherwise, we're going to continue on. All right? There is something called a sodium-potassium exchange pump. And the sodium-potassium exchange pump is in the membrane of the cell, of the neuron, okay? And remember that cell membranes are semi-permeable. So you're going to have a pump that is going to allow things to pump in and things to pump out. And if we're talking about that sodium and we're talking about that potassium, the sodium-potassium exchange pump is going to move those molecules when it's necessary, all right? So those are going to be in the semi-permeable membrane. And I'm drawing these little yellow dots here, these little yellow lines to show the little channels that go in between the inside and the outside of the cell. All right. Now, all of those yellow lines represent multiple things because in the membrane of the neuron, you're going to have open channels that allow chemicals to move freely. You're going to have voltage gated channels that are going to open with the positive current that's going to flow through. When I say current, there's an electrical current that's going to flow through these neurons. Okay, and so these channels work a little bit differently depending on what kind of channels they are. Okay, a cell membrane more permeable to potassium than sodium. It's going to let the potassium go in and out, but not the sodium. So through some of these channels that I drew, that potassium is going to be able to move out freely. And we are going to have potassium on the outside as well as on the inside, okay? And potassium is able to flow wherever it needs to. And there's something called a concentration gradient. Things flow from areas of high concentration to areas of low concentration. So when you have lots of potassium inside, it's going to flow outside. When you have lots of potassium outside, it's going to flow inside. And it's going to do that until it reaches what we call equilibrium. All right. Now, the sodium cannot go back and forth like the potassium. The sodium is controlled. All right. Um, okay, so number 3 there, we already talked about some of the potassium is going to diffuse out of the cell while negative ions remain inside, therefore it is polarized. This is a representation of an axon that is polarized, meaning that's positive on the outside and negative on the inside. All right, so this concludes this section on the cell membrane at rest. Now, something's going to happen. What's going to happen? We're going to have an action potential come through. All right. And when that action potential comes through, we are going to have voltage gated channels open. Those little yellow dashes that I drew are going to open, and that's going to allow the sodium to rush in. And when the sodium rushes in, the inside of the membrane is going to become positive because there will be more positive ions at that point, and that negative environment will turn positive. And when we have positive outside and we have positive inside, we now have depolarization. All right. So it's really important that we understand depolarization is the idea that the sodium has rushed in and now there is no longer a positive and a negative at that section of the neuron. Okay. So what's going to happen is the potassium is going to leave the cell rapidly in order to try to regain the balance. Okay, so if I have all of the sodium rushing in, well, that's going to take up a lot of space, and the potassium is going to get pushed out those gated channels or those channels in order to try to balance out the equilibrium. Okay, and at that point, we are going to end up with repolarization because as those positives get pushed out, the balance between positive and negative is going to return to a negative state. We now are going to have negative on the inside, positive on the outside. It has now repolarized. Okay, so super important that we realize when this happens, we now have the sodium on the inside and the potassium on the outside. And if you remember the resting potential that you're looking at right now, the sodium is in higher concentrations outside. So we now have these chemicals in the wrong place. The last step is going to be, I'm sorry, I said the last step. We're at number 4. The sodium potassium exchange pump is going to rapidly pump the sodium out and pump in the potassium in order to restore the axon to the resting potential. All right. So, the other thing, part 5, that you need to know is that when one part of the cell depolarizes, it's going to cause a change in the parts next to it. Okay. So, for example, um, I don't have a good example. I'm going to show the video now, okay?
A nerve impulse is an electrical current that travels along dendrites or axons due to ions moving through voltage-gated channels in the neuron's plasma membrane. Voltage-gated channels open and close to an electrical voltage, so they are affected by changes in electrical charge around them. When a neuron is at rest, a charge difference is maintained between the inside and outside of the cell. This charge difference is produced and maintained largely by active transport using sodium-potassium pumps. The pumps send sodium ions out of the cell and bring potassium ions in. While other channels allow some flow of potassium ions back out of the cell, the sodium ions cannot easily get back in to replace the lost positive charges. The overall result is that the exterior of the cell has a net positive charge and the interior has a net negative charge.
Okay, sorry for the
The
hiccup.
difference in
It says
charge
we're still
between the
recording.
interior and exterior of the cell is called the resting membrane potential. A nerve impulse begins when a stimulus disturbs the plasma membrane on a dendrite, causing sodium channels to open. Sodium ions flow into the cell, lessening the charge difference at that location. If the change is enough, it will cause nearby voltage-gated sodium channels to open. This allows so many sodium ions to flood into the cell at that location that the membrane there is depolarized, with the local region inside the cell having a net positive charge and the outside of the cell having a net negative charge. This affects neighboring voltage-gated sodium channels, which then open, moving the depolarization along the membrane. This moving depolarization is called an action potential. Changes occur behind the action potential to restore the resting membrane potential. The voltage-gated sodium channels close and voltage-gated potassium channels open. This allows a rapid flow of potassium ions out of the cell, repolarizing the membrane so that the inside is again negative and the outside positive. This is followed by use of sodium-potassium pumps to fully restore the resting membrane potential and to reestablish proper concentrations of sodium and potassium ions inside and outside the cell.
How does an action potential occur? When a neuron is not transmitting a signal, there is a separation of charge across its membrane. This is called the resting potential. Sodium is in high concentration outside, and potassium is in high concentration inside the cell. The cytoplasm is negative relative to the exterior because of the presence of negatively charged proteins, amino acids, and other
Okay,
substances.
so hopefully that
When a
makes a little
sufficiently
bit more
large
sense.
stimulus reaches a section of membrane,
I
sodium
did
is able to
have
diffuse in
another
across the
video
membrane
here
following its
that I
concentration
wanted to
gradient.
show you,
This depolarizes the membrane
and
and is the stimulus for similar changes
would
in
it be in my
adjacent membrane.
library?
Thus, the action potential travels down
I
the
have
axon
3
in a
neuron
chain reaction.
videos. Here is the other one I
After
wanted you to
sodium
see.
diffuses in, potassium diffuses out, following its own concentration gradient. This restores the membrane's polarity, but sodium and potassium have switched positions. The sodium-potassium pump restores these ions to their original positions, and the neuron is now ready for another action potential.
Okay, so we now have this idea of an action potential and what is happening during the passing of the impulse. Okay, again, an impulse is going to be what travels through the neuron. All right. Um, Please know that neurons only send messages in one direction. So you have all of your afferent neurons going towards the brain, and you have all your efferent neurons coming away from the brain. Okay. And the two will run right next to each other in the ganglia of your body, in the areas where the neurons collect. Okay. But it's really important to know that they're only going to go one direction. Excuse me, they're only going to go one direction, and they're going to go in that direction, like I said, up to thousands of times per second. Okay, so super important. What's going to happen when the transmission, when the impulse reaches the end of the neuron? I want you guys to know that our next video will be regarding the synapse. And the synapse is going to be what I am drawing in yellow here at the end of the neuron, at those synaptic terminals. Okay, so a neuron can only be connected to a few things. Another neuron, you have 100 billion neurons in your brain. Okay, it can also be attached to a gland. So if your body's needing to release hormones, all right, it can be attached to a muscle telling you to move. It can be attached to organs causing you to digest your food, right? Your stomach's going to contract and undulate in order to move that food around in your stomach.